This is a brief summary of a brief report that came out in Nature Climate Change. The context is that 2023 is getting a lot of attention for projections that this will be the warmest year on record thus far. Of course, there is an El Nino going on, which we know is a mini global warming and emits or throws out ocean heat into the atmosphere and causes temporary warming. There are other modes like the Atlantic multi-decadal oscillation and so on, which can do that. So here is the result from the latest NOAA Global Climate Report, which looks at June to August temperature anomalies and shows that up to now, at least for this season, we have been at just under 1.2 degrees C in the global land and ocean temperature anomaly with respect to the baseline, which obviously doesn't really matter in terms of shifting the baseline and getting slightly different numbers. So what are the candidates to add to this spike in warming in 2023? Obviously, the wildfires have been big news. Canada created lots of news with record wildfire area burned, extent, duration, and the emissions, which drifted all the way down into Northern America, and there have been wildfires across Europe and some parts of Asia as well. So this is the result from running a model, cumulative daily fine carbon emissions for Canada in 2023 and annual total fire wild carbon emissions compared to other years. And you can see that the data, or at least the model simulated cumulative total fine carbon in terms of total wildfire emissions and millions of tons of carbon. We are looking at the 2023 here shooting off into La La Land for 2023 and the 2003 to 2022 average with the ranges is shown here. So that's for these other years have future data. I mean the total year data, of course, whereas when this report is being created, we had wildfire estimates only up till here. There are similar estimates in this Copernicus report for Europe and I think also Russian wildfires, for example. So this is the annual total wildfire carbon emissions for Canada itself, not the other countries. You can see that 2023 is off the charts here, and this is only up to September 10th, so fairly recent. With that in mind, this short report in Nature Communications is very interesting. Tonga eruption increases chance of temporary surface temperature anomaly above 1.5 degrees C. As we know from our previous discussions in various courses, volcanoes tend to cool the climate, and there are famous events from before which caused the year without summer and so on. But if the volcano happens to be in a special place below sea level, throwing up a lot more moisture, especially into the stratosphere, then you have a very strong global warming greenhouse gas, and in the stratosphere it can stay for a long time, as we know from the physics and circulation of the stratosphere, which also I have discussed elsewhere. Let's read the abstract, look at a couple of figures and the summary to make this brief point. On 15 January 2022, the Hunga-Tonga Haipai, so HTHH for affectionately short form, this eruption injected 146 million tons of water and 0.42 million tons of SO2 into the stratosphere. What's special about this? This large water vapor perturbation means that HTHH will probably increase the net radiative forcing, unusual for a large volcanic eruption, increasing the chance of global surface temperature anomaly temporarily exceeding the 1.5 degrees C over the coming decade. Here, we estimate the radioactive response to the HTHH eruption and derive the increased risk that the global mean surface temperature anomaly shortly exceeds 1.5 degrees C following the eruption. We show that HTHH has a tangible impact of the chance of imminent 1.5 degree C exceedance, increasing the chance of at least one of the next 5 years exceeding 1.5 degree C by 7%. So there is the emissions trajectory we are on, and that's bringing a certain rate of warming. So this is exceeding that rate by additional 7% because of the water vapor emitted by the this particular volcano, and this amount of sulfur is much lower than what typically happens during an El Nino, did I say? Because of the volcano. And this amount of sulfur dioxide is lower than what generally happens. Sulfate is a scattering aerosol and actually what causes the cooling. So this year this particular volcano is special in that sense. Okay, but the level of climate policy ambition, particularly the mitigation of short-lived climate pollutants, dominates the 1.5 degree C exceedance outlook over decadal timescales. Okay, here are the calculations. I won't go too much into the details, but obviously a model is used to do future emissions for the short term here, using various scenarios which we have discussed elsewhere. SSP2 is shared socioeconomic pathway. 45 corresponds to 4.5 watts per meter squared additional radiative forcing by 2100 if we follow this pathway, and so on. So 1.9 is the one that's expected to keep us below 1.5 degrees C by 2100 with 67% probability. So here are the temperature anomalies with relative to the baseline 1850 to 1900. So that's kind of the IPCC report showing the range here. So there are emissions, the projections excluding HTHH, so that's in this grayish line. You can see multiple realizations, and you have the upper and lower bounds from 2020 onwards where we are heading. So this is where the eruption actually happens, so just pay attention to where we are headed, especially these lines as the means of the ensembles. And this is including HTHH, so that's the green line, so slightly above the gray line. And if we go to, that's the middle of the way pathway, SSP2 4.5, so there the emissions are higher. But if we consider the lower emission scenarios of SSP1 1.9, again 1.9 is the net radiative forcing, additional forcing by 2100. So excluding and including HTHH, you can see that by 2030 we are likely to exceed the 1.5 degree C target, even if we are ambitious and somehow found a way to getting to this pathway, which we are not on right now anyways. So either way, I would say we are likely to cross 1.5, but this is just about what the volcanic eruption would do, considering its special character of throwing up so much water vapor, which is a strong greenhouse gas. And it would easily rain out if it's in the troposphere, but it's in the stratosphere, and that's why it can have long-lasting effects. So this is the chance of crossing 1.5 degrees C going into the future. So you can see various probabilities here, and you can track the various scenarios. So we are looking here at the likelihood of global surface temperature anomaly exceeding 1.5 degrees C between 2015 and 2035, which are the solid lines, and the cumulative probability that no year has yet exceeded 1.5 degrees C in this dashed lines. So essentially the cumulative probabilities drop off at some point, and the probabilities of these various scenarios exceed these probabilities as we come towards 2030, which is basically showing you what are the probabilities of crossing these when we include or exclude the emissions. So the shaded ranges show uncertainties in the 2022 to 2026 1.5 degree C exceedance risk. So it's a very careful study in that sense of using multiple scenarios, doing simulations with and without the volcanic eruption, and accounting for probabilities and also uncertainties, which is always critical. So very brief, but while the HTHH eruption produces a measurable change in the probability of imminent 1.5 degree C exceedance for any given scenario, human choices still dominate the decadal risk outlook. So they are optimistic that we are still in control. Further crossing the 1.5 degree C in a single year does not mean the Paris Agreement has failed. Another optimistic message. Although exposure to climate risk increases the elevated GMST global mean surface temperature regardless of cause, exceedance of temperature thresholds in the Paris Agreement is based strictly on the anthropogenic contribution to GMST. This is critical because IPCC reports cannot tell you precisely which year will have a combination of El Nino or El Nino and wildfires or El Nino and wildfires and volcanic eruption with special emissions of water vapor in the future to have these spikes, and how long they will last and come back. What will be the impacts if we exceed 1.5 degrees C for a year or two? Will this somehow create some local or global impact that's way beyond what we are already seeing? So all these are key critical questions. So keeping that in mind, natural forcing and the climate system's internal variability does not play a role in dictating whether these thresholds have been crossed. Despite this, the HTHH eruption does not temporarily increase the GMST anomaly over the next 5 years, while stratospheric water vapor concentrations are perturbed. Over this period, HTHH increases the likelihood that we observe our first 1.5 degree C year by about 7%. Okay, so keep that in mind, and it's useful just because they are very careful in the way they do this without raising alarms and screaming that the world is coming to an end, which are the kind of reports I always like because they remain much more tempered by scientific findings and their uncertainties, especially when you use models and go into the future with all these scenarios which are supposed to cover the all the possibilities, but we know that in the short term internal variability dominates. So if we are increasing volcanic eruption forcing, which is an external forcing, then we are adding to the external forcing by human beings in terms of increased greenhouse gases, and this doesn't even consider the wildfire emissions, which somebody else will do, I'm sure. Okay, I will leave this here.